Hello everyone, good afternoon. I'm Beer-Lambert, one of the specialty registrars in chemical pathology at Imperial. So I have been asked to talk on spectrophotometry, especially focusing on ST rays. So during next 30 to 40 minutes, I will be covering introduction to optical techniques, spectrophotometry, reflectance photometry, turbidimetry, and nephelometry, and atomic absorption spectrophotometry. Let's start with a basic question to get us thinking. So which of the following biochemical analytes I have mentioned here measured using optical techniques? So here is the answer. So except serum potassium, sodium, and serum chloride, so all the other biochemical analytes are measured using optical techniques. The nature of light. So electromagnetic spectrum covers a wide range of wavelength from radio wave to one end and to the gamma rays in the other end. However, we are particularly interested in UV rays, the visible spectrum, and the infrared spectrum. So here I have mentioned the wavelength of the UV rays when it is less than 380 nanometers, and the visible spectrum range from 380 to 750, and the infrared spectrum when it is more than 750 nanometers. So currently, there are several optical techniques are being used in the clinical chemistry, and the principle behind these optical techniques mainly depend on the fate of the light in a reaction cell. As an example, in spectrophotometry or else atomic absorption spectrophotometry, we are using the concept of transmission or the absorption. And in nephelometry or turbidimetry, we are using the fate scattering property. And in reflectance photometry, it is the reflection we are using. So before moving to the spectrophotometry, I would like to ask the second question. So from these biochemical analytes, can you guess for which we are using the spectrophotometry? So apart from CRP, lipoproteins, and urine albumin, so all the other biochemical analytes are measured using spectrophotometric technique. The principle of spectrophotometry. So the photometry is the measurement of the light, and the spectrophotometry is the measurement of the intensity of light at a given wavelength. So the spectrophotometry is widely used in quantitative as well as the qualitative analysis. So the method depends on the light absorbing property of the analyte of interest or the derivative. So it's most of the time it will be a derivative. As an example, in a glucose method, so commonly we are using the hexokinase method. So in hexokinase method, we are not directly measuring the glucose concentration. It is the NADH concentration we are using. The basic concept. So the incident light beam is denoted as I naught, and the intensity of the transmitted light beam is denoted as IS. So the transmittance through the test cell will be equal to the IS divided by I naught. However, the portion of incident light can be absorbed or reflected by the cell wall or the solvent. So to eliminate this error, so we can correct it using the reference cell. So the reference cell will be identical to the sample cell except the chromogen of interest. So the transmittance through the reference cell will be equal to IR divided by I naught. So if we correct the error, so the transmittance for the compound of interest will be equal to the IS divided by IR. So the spectrophotometry actually measures the transmittance. So as you can see here, the problem with the transmittance is because the transmittance varies inversely and logarithmically with the concentration. So because of that, for the convenience, we are using the concept absorbance. So the absorbance is, as you can see here in the other graph, so that is directly proportionate to the concentration. So the absorbance will be equal to the minus log T. And if we take the percentage of transmittance, so it will be, absorbance will be equal to the 2 minus log T in percentage. So it's better if you can remember these two equations. So Beer-Lambert law. So the Beer-Lambert law is the fundamental to the spectrophotometry, and it is the result of work by Beer and the Lambert. So it states the relationship between the absorbance, molar absorptivity, light path, and the concentration of the absorbing compound. Few words about the molar absorptivity, which is also known as the molar extinction coefficient. So this value is a constant for a given compound at a given wavelength under pre-specified conditions of the solvent, such as temperature and pH. So that this value can be used to characterize the compound and to establish the purity, and also to compare the sensitivities of the measurements obtained on derivatives. The applications of the Beer law. So in practice, we establish the relationship between the absorbance and the concentration using the series of calibrators. And the linear relationship here, so that is exists up to certain concentration. So when this linear relationship exists, so the solution is said to obey the Beer law. So within this limit, we can use the calibration constant K or the calibration graph to obtain the concentration of unknown solution. And the Beer-Lambert law is followed, only these following criteria are met. So the incident radiance should be monochromatic, and the solvent absorption should be insignificant compared to the solute absorbance, and the solute concentration should be within given limits, and there should not be any optical interferences, and there should not be any chemical reaction between the molecule of interest and other solute or solvent. So let's do two simple calculations. So the first one, so when the PO bilirubin dissolved in chloroform at 25 degrees of Celsius, so the molar absorptivity is 60,700 at 453 wavelength, and the molecular weight is 584, and the concentration of the bilirubin is 5 milligrams per liter. So what is the absorbance? So this is the straightforward calculation. So here you can substitute this value to the Beer-Lambert law and calculate the absorbance. But here you should be cautious when you are substituting the values, because in the calculation, they have mentioned the concentration in milligrams per liter. So when you are substituting the values to the Beer-Lambert law, so you need to mention the concentration in the moles per liter. So you can calculate the concentration with using the molecular weight. So let's move to the second calculation. So the transmittance of a solution of NADH at 340 nanometer is 45%. So they are giving the transmittance in percentage. So what is the absorbance at 340 nanometer of a 1 in 5 dilution of this solution? So here they are asking the solution which is diluted, and the diluent factor is the 5. So we can calculate the absorbance from the previous equation I have mentioned. So the absorbance equal to 2 minus log T in percentage. So we can calculate the absorbance of the first solution. And then as the Beer-Lambert law states, so the absorbance will be directly proportionate to the concentration. So the second solution concentration, we can take it as the dividing by the diluent factor. So it is 5. So you can calculate the absorbance in the second solution by dividing the absorbance, previous absorbance, by 5. So these calculations are straightforward. So if you can remember these equations. So let's move to the instrumentation. So when the beam of light passes through the monochromator, so it isolates the desired region of the spectrum, and then it passed through the absorption cell, which is known as the quet. And so here the portion of the radiant energy is absorbed depend on the nature and its concentration of the analyte of interest. And any light which is not absorbed here, it is transmitted to the detector. So in the detector, so it is converted to electrical energy. So there are mainly two types of spectrophotometer, the single beam spectrophotometer and the double beam spectrophotometer. So the principle behind the single beam spectrophotometer is exactly what I have described now. And in double beam spectrophotometer, what is the difference is there is a light beam chopper behind the exit slit, and with the use of system of mirrors, so the light is reflected through this sample and as well as the reference cell at the same time and then to the detector. So this compensates any light source variation and as well as the sensitivity changes in the detector. So the light sources, so there are mainly two types, this is incandescent lamps and the laser source. So what we are using in the visual region is the tungsten bulb, and the quartz halogen lamp is the modified version of the tungsten bulb. So it is modified with use in the low pressure iodide or bromide and also covered with a fused silicon envelope. So the lifetime will be increased compared to the tungsten bulb. However, the tungsten bulb of the quartz halogen lamp not supply the sufficient energy for the measurement of UV range. So because of that, for the UV region, we need to use the hydrogen and deuterium lamps, high pressure mercury lamps, or xenon arc lamps. I would like to highlight the main three properties of the laser source. So it's because of its spatial coherent and its monochromatic light, and also it having a very narrow pulse width compared to the conventional light sources. Spectral isolation. So here the desired wavelength of the radiant energy is isolated. So as an example, so if the light source producing the light containing blue, green, and red light, and if you want to isolate only the green light, so you need to choose a monochromatic system which isolate only the green light and filtering out the blue and red light. So there are mainly three types. So the simplest one is the colored glass filter, and the prism and diffraction gratings are widely used in monochromators. So the spectral purity of the monochromator, so it's described in terms of spectral bandwidth. So, and if we take the spectral transmittance curve, so the spectral bandwidth is the width in nanometer at the point equal to the one half the peak transmittance. So this is the spectral bandwidth of this monochromator. And there's another concept which is called natural bandwidth of the absorbing substance. So that is described in terms of the spectral absorbance curve of the absorbing substance. So what is the importance of this concept? Because the accuracy of the measurement depends on the ratio between the spectral bandwidth to natural bandwidth. So the lower the ratio, as you can see here, so the lower the ratio, so the better the accuracy. That means the lower the narrow the bandwidth, so the better the accuracy. The quet, so this is a small vessel to hold the liquid sample in the light path of the spectrophotometer. And this can be round, square, or rectangular. And most of the time, light path length will be 1 centimeter. And for the visible range, we are using commonly the ordinary borosilicate quets. And for the UV range, it's quartz quets. And the plastic may have good clarity in both visible and UV range, but the disadvantages are the tolerance, cleaning, temperature, and chemical etching. And especially when we use quets in the UV range, we should be more cautious because invisible scratches and fingerprints and also residual traces may cause significant change in the absorbance in UV range. So the photodetector, so this converts the light into an electrical signal. in proportionate to the number of photons. So there are mainly two types, photomultiplier tube and the photodiode. So as you can see here in this diagram, so in the photomultiplier tube, it consists of a cathode, so which is photosensitive, and also series of diodes. So as the photon striking on the cathode, so it emits electrons. So these electrons are accelerated to the each diodes. So at each diode, so the electrical signal will be multiplied. And at the end of the anode, you will get an amplified signal. So in the photodiode, so it is a solid state photodetector, and it is fabricated from photosensitive semiconductor material. So this semiconductor material is responding to specific wavelength. And the photodiode array is consisting of 2D arrays of diode series. And to verify that your spectrophotometer is functioning satisfactory, you can use these performance parameters: the wavelength accuracy, stray light, photometric accuracy, spectral bandwidth, linearity, multiple wavelength checks. So I'm going to talk about the second analytical technique. So this is reflectance photometry. So here the diffuse reflected light is measured. So here, if it is, this is the reaction mixture. And if it is illuminated with the diffuse light from the light source here, so the intensity of the reflected light from the chromogen is measured from the detector. So the instrumentation wise, it is more or less similar to the spectrophotometry, but the difference is the geometry of the system, because here light source as well as the detector are on the same side. And the problem is the reflected light intensity is non-linear in relation to the concentration of the analyte. However, we can use certain equations such as Clapeyron-Williams transformation to convert this data into a linear format. And the dry slide technology and this transcutaneous bilirubinometer, so in these two techniques, we are using the reflectance photometric technique. The nephelometry and turbidimetry. So here they are used to measure the scattered light. And currently, these techniques are commonly used to measure various kind of proteins, such as urine and CSF proteins. And immunoturbidimetry technique, we are commonly used to measure the CRP, lipoproteins, urea albumin, and fecal calprotectin. A few words about the factors influencing the light scattering. So the factors are the particle size, wavelength dependence, distance of observation, effects of polarization of incident light, concentration of the particles, molecular weight of the particles. And depending on the particle size and the wavelength dependence, so they have mainly described three types of scattering: Rayleigh, Rayleigh-Debye, and Mean scattering. The turbidimetry versus nephelometry. So in turbidimetry, instrumentation is quite similar to the spectrophotometry. As you can see here, so the detector is oriented at 180-degree angle in relation to the incident light. And the reduction in the intensity of the light due to the scattering is measured. However, in nephelometry, the detector is oriented at an angle at the 30 or 90 degree, and the incident of the intensity of the scattered light is measured, and this intensity of the scattered light is directly proportionate to the concentration of the analyte of interest. So the choice of between the turbidimetry and nephelometry depends on the application and availability of the instrument. Because if you want to establish a new method, depend on the turbidimetric technique. So you don't need to buy a new analyzer if you have a spectrophotometric automated analyzer. But if you want to establish a new method, depending based on the nephelometric technique, you need to buy a new analyzer. However, the nephelometry still offers some advantage in terms of sensitivity because it measures the scattered light intensity against the black background. So atomic absorption spectrophotometry. So this is the last optical technique we are going to discuss today. So atomic absorption spectrophotometry is widely used in clinical laboratory to measure the metal elements such as copper, lead, lithium, aluminium, especially in related to the heavy metal poisoning. However, currently, ICP-MS is replacing its clinical use in clinical laboratory. So when it comes to the instrumentation, so this holocathode lamp, which is the light source here, consists of a cathode. So this cathode is made up of the material to be analyzed, and it will produce a wavelength which is specific for the metal atom of interest. And the sample here, it is introduced to the flame by using the nebulizer. So this sample containing the interest metal will be introduced to the flame. And inside the flame, this metal will be atomized. However, it is not excited. So this metal atom will be in the ground state. So this ground state atom will absorb the specific wavelength, and this results in the net reduction in the intensity of the transmitted light beam. So this reduction will be measured by this detector. So during last 30 to 40 minutes, I have gone through these topics, but this is just a basic overview of these optical techniques. And you can refer Teach textbooks of laboratory medicine and Kaplan clinical chemistry, and as well as for the calculation Deacon's challenge for more information. Thank you.